This is the prep packet video for Unit 4, Chapter 9.3. We're working now on Objective 5, where we simplify square root expressions containing variables with odd exponents. So before we looked at the idea of working with a square root expression that had an even exponent. So we took the square root of x to the 6th was the same as x to the 6 over 2 x to the 3rd. Now we're looking at square root expressions that have odd exponents. So it would be the square root of x to the 3rd. We can use the product rule for radicals and fractional exponents to help us understand this. Remember, the product rule says that the square root of x to the 3rd is the same as the square root of x to the 2nd times x, because that's secretly x to the 1, and 2 plus 1 is 3. So if you start out with x to the 3rd and you end up with the product of x to the 2nd times, or the square root of x times the square root of x to the 2nd times the square root of x, what you're going to end up with, you can take the x out of that, and you'll have x times the square root of x. Now, there's a slightly easier way to do this, and it involves our old friend short division. So if I have this, and remember I have a secret 2 here, this is the same as x to the 7 over 2, right? Well, that is 2 goes into 7 3 times with 1 left over. If I have the square root of, and I'm writing the index here just to make a point, if I have the square root of m to the 11th, that's the same as, oops, I'm not using x though, I'm using m. That's the same as m to the 11th over 2. And 2 goes into 11 5 times, and it leaves behind just 1. So little 2 there. 2 times 5 is 10, and 10 plus 1 is 11. This will make more sense as we have some more practice with it. So again, what you're looking at is, this is sort of a longer way of doing it. Here you're using it as a division problem to the side. So there's your index, and there's your index. And there's the power of the radicand and the power of the radicand. So they're saying that 2 goes into 7 3 times, and the remainder is 1. So what you'll end up with is that 3 there, and the remainder is the one that stays inside, the radicand. Here it is again. We have the index is 2. The radicand, the power of the radicand is 11. And what you end up with is 2 goes into 11 5 times. There's the 5. And the remainder is 1. And that is what gets left behind. Let's take a look here. Now again, right now we're just working with the square root, so it's just the index is 2. And again, that's understood. And the power of the radicand is 9. So what I'm going to look at is 2 goes into 9 4 times with 1 left over. So I will rewrite this as m to the 4th, because that's what came out, and what got left behind was this guy. So what's left inside the radical is just m. Here's one that's a little with a higher power. So here's the square root of, again, it's that silent 2. So I'm going to divide by 2. And the power in the inside the radical is 13, so that's going to go there. And it kind of gives you a picture too, is that just like you're used to with a division problem, the 2 is on the outside, the 2 is on the outside, the 13 is on the inside, the 13 is on the inside. So 2 goes into 13 6 times, and the remainder is 1. So that means once I go to rewrite this, it will have t to the 6th on the outside and t to the 1 on the inside. I'm going to show you one that's not with a square root because it might help you make more sense too. So if I have I need to find the 5th root of x to the 16th. So I'm going to take this on the outside of the division problem, and on the inside will be this, right? 5 goes into 16 3 times. So on the outside, I get to pull this out of the radical, will be x to the 3rd. And what's left in is the remainder of 1. You might be wondering why that works. Well, let me show you. So if I have the square root, let's take the cube root. The cube root of x to the 17th. Well, that's asking me to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I'm looking for 3 of a kind, because for every 3 that are inside the radical, 1 gets to come out. So there's 3, there's 3, there's 3, there's 3, there's 3. Oh, 2 left over. So what do I have up here? I have x to the 3rd. Sorry, I have an x came out, right? For every 3 inside, I get 1 outside. So that's 1, 2, 3, 4, 5. So that's x to the 5th, and I have 2, and they can't come out. They have to stay in there. So that's x squared. So that's just it. That's what the picture of what we're doing looks like. Let's test it and see what happens. If I do 3 into 17, 3 goes into 17 5 times with 2 left over. So I would have x to the 5th. That was a poor color choice. And x to the 2nd inside. And that's kind of why that works. Let's take a look and see if we can do this. Oh, okay. So we've seen this one before. Well, b to the 2nd, the square root of b to the 2nd is b. But let's take a look at the square root of k to the 5th. And again, I have my secret 2. You can draw the picture. There's 5 k's. How many 2's can you make out of that? 1, 2. So that would be k to the 2nd, and you leave behind a k inside. Let's do the math. 2 goes into 5 2 times with 1 left over. And again, that's an unspoken 1. I can make one up. I'm brilliant. I can do this. So I have the square root of x to the 23rd. So I could draw 23 x's, but I don't really need to, because 2 goes into 23 10 times with 3 left over. So I will have on the outside x to the 10th times the square root of x to the third. And how can I test that? Just like this. 2 times 10 is 20, plus 3 is 23, and that is what I started with. Obviously, you know by now how to stop and copy, go back and review, but I want you to also do the U-tries on page 540 and 541. Make sure you include this work with your prep packet. And that's it for this one. See you in the next video.